Good afternoon. My name is Bill Austen, and this afternoon I'll be talking about some work we're doing simulating collisions between small drones and manned aircraft, and in particular, how we're using the cloud to support this work. Although today's presentation focuses on the potential threats posed by drones, I wouldn't want to leave anyone with the impression that this reflects our position on drone technologies. In fact, QinetiQ are responsible and involved with all aspects of drone design and operation, from design and development of systems and payloads to the operation of drones, to defense against drones for unintentional incursions, supporting our customers in using drones, providing training and through life support, and of course on education through STEM, university and professional institutions. Our particular interest in collisions started around about 2016, when we undertook a programme to evaluate drone collisions against multiple different fixed wing and rotorcraft windshield structures. This was a fast-paced programme that was exciting, challenging, and indeed pretty stressful at times, because all the data that we generated and the methods and the testing facilities had to be generated pretty much from scratch, evaluating events that had not previously been explored in pretty much a world-first programme. The programme itself, which included simulation and full-scale collision testing between drones and aircraft structures, was highly successful, with the results correlating well between our testing and upfront modelling against a wide variety of different impact scenarios. Of course, some time has passed now, and the simulation techniques have been continued to develop, including keeping pace with more modern drone designs, which have become rather more complex than the early days. Also, our testing capabilities have also advanced, which allows us, with our testing partners, to confidently launch drones at a range of different speeds in a safe and controlled environment. Video that was playing then, and I'll just try and start again. Oh, if it doesn't just pause, let me just get that. Yeah, the video is just playing there, is an example of a collision against a windshield structure. I should point out, however, that the beauty of simulation is that we can replicate a wide variety of events, including changing the speeds. In this case, I would describe this as a high-speed impact, and I wouldn't want anyone to leave with the impression that this is necessarily how all drone collisions end, but it is quite a nice one for showing some dramatic effect. So, on to our current programme for EASA. So this is a 3-year programme for the European Union Aviation Safety Agency. The programme itself is sponsored by the European Commission under the Horizon 2020 framework, and the 3 primary objectives include a deepening of understanding in the effects of collisions between a range of different mass market drones and different classes of manned aircraft. After this, having developed all this knowledge, we're then going to be looking at whether there are practical steps that could be made to mitigate the potential severity of impacts by changing by the inclusion or exclusion of design features on each of the drones. So are there changes that could be made to drones to make them safer in the event of a potential collision? And then looking at whether there are any drafting some design requirements and test standards for future drones for sale in the EU. The programme itself is large, and we could talk a lot about each of these tasks. There's 9 tasks within the activity, but today we're going to focus down on a couple of really small elements of it. First of all is the development of the threat models, or the drone finite element models, and we're also going to touch on a little bit about the simulation of the collisions themselves. So onto the drones. Our early work in the programme identified 5 different consumer drones that are of potential interest to and within scope of the programme. These were selected to cover a reasonably broad common mass range from around about 1/4 kilo up to approximately 3.5 kilo configurations. And the individual drones were selected based on either them being sort of highly ubiquitous design or a single product or indeed product family, or them being representative of a common class in which there may be a number of products of similar configuration. In order for us to do the collisions or the simulation of the collisions, we therefore need to generate accurate and validated drone models. And so this now reflects the almost virtual fleet of drones that we've processed and have validated models for. So what I'm going to talk about now is just a few of the steps that goes into the development of these different drone models. Typically, we start off with a 3D scanning methods where we get accurate 3D scan of the external shape of a product, but also we disassemble it and get accurate scans of the constituent components and subassemblies. These are then turned into a simplified CAD model that we can import into Abaqus CAE to process the mesh and start to do arguably the real work on it. There are a number of components in these complex assemblies. Some of them are represented as plastic shells or circuit boards with masses for circuit for the electronic components. But we pay particular attention to some of the heavier or stiffer items, such as motors, batteries, or camera assemblies. So as an example of one of these, a motor, although it's shown in the main image there as just being a single component, actually it's a sub-assembly of parts that we've created to replicate the internals of that motor. So why go to so much trouble? Well, it's all very well just adding lots of detail, but it's always got to be for a reason. And in this case, what we're trying to do is make sure that when our components and our whole drones are impacted targets, the force that they impart on the structure is accurate. So what we do, having generated these models, we do a range of different calibration and validation tests. These typically start out with some static crush tests with uniaxial machines, where we compare the crush response, the force displacement response of the components against our simulated surrogates. We then move on to a more complex test, and these are some images from an impact scenario where the motor's being fired at an instrumented Hopkinson bar. The motor's fired in from the right, and we see here different time intervals of the impact event. From these, we're comparing not just the physical behaviours and how much the motor has been deformed, but critically, we're also extracting the force time response as the motor hits the target. What we see here in the blue is the results from the test, the force time response from the test, overlaid with the analysis predictions for that same scenario, which is obviously modelled alongside the test conditions. So of course, this is repeated a number of times for the different drone components, the motors, the batteries, the camera systems for each of the drones. But to validate the entire drone as a complete threat assembly, we then do a similar test where we can, where we're launching a whole drone against the same instrumented target. And this just shows a few still images taken from the high-speed photography of the model on the left versus the test on the right. So here we see the crush response, the impact behavior, looking all very nice, doing the right kinds of things. And alongside this, we extract the force time curves, and that's used just to validate our final drone model before it's used for simulation of real events. So what's all this got to do with clouds? Well, the current activity we're up to, which is task 5 in the program, this involves assessing a wide variety of different collision scenarios, involving multiple different drones, impacting different categories of aircraft on each of those different impact locations, which might include windshields, leading edge structures, propellers, or main rotors and tail rotors of rotorcraft. These were all down selected in an earlier activity. The assessment includes a combination of analysis and test, and the test aspects within the program broadly fit within a kind of test pyramid, standard test pyramid, where the lower level, smaller scale tests, which might be characterization of components or validation of target materials. There's quite a lot of those, and they form the bottom bedrock of that pyramid. But as we get to the top of the pyramid, where we're wanting to generate real results, impacts of drones against real bits of aircraft structure, they are fewer in number. However, simulation is obviously a lot more scalable. And what was a test pyramid turns into more of a modeling mushroom, where at the lower end, it mirrors the test pyramid. Obviously, we model the same conditions that we're testing. But as we get to that top end, where we're looking at real collisions between whole aircraft or sub-assemblies of aircraft, that's where we scale up the models to generate more results and more value. But of course, this requires considerable computational effort. The first half, 18 months of the programme, have been subject to some delays due to national lockdowns and other COVID-related disruption. So of course, now we're looking at ways in which we might be able to regain some lost time, but without compromising on quality. Looking at some of the processes, the model generation and validation, well, that's quite difficult to accelerate. It requires skilled people who are familiar with the activities. Likewise, the setup and post-processing, well, here we've made some really good ground developing custom scripts to take a lot of time out of those post-processing activities, and those have been developed over many years. Where the opportunity for us lies is in addressing the bottlenecks in solving these models. And if we can tackle that, then it enables greater value from the investment that's gone into those simulation methods and expands the top of that modeling mushroom. And this is where the 3D Experience cloud compute solution really comes in. So just to set the scene, QinetiQ are already pretty heavily invested in Simulia licenses and also hardware to run them. But our holdings are naturally sized around our more normal research operations. So where we get peaks in demand like this, it naturally results in bottlenecks. The new 3D Experience Cloud Compute is a flexible service that provides the simulation, additional simulation capacity on demand. And as I was looking at it, my take on it is there's two really good reasons to consider this. The first is on job scaling, where maybe you've got a large simulation that's not running well or can't run on on-site hardware or with on-site license restrictions. That's not really the case that we've got here. Because the capability we've developed, or the drone modeling techniques, they're sized around our computational system. What's more applicable to us is on throughput scaling, where the use of the cloud will enable large batches of jobs to be executed in parallel, rather than just individual jobs or small numbers of jobs in parallel. This allows us to set up a whole batch together. We've recently been trialing this service to make sure that it fits the workflow of the project. And as a result of this, we're aiming to start using it properly from the end of December, beginning of January, which is when we see that bottleneck, solver bottleneck starting to bite. The service itself is accessed through the 3D Experience web interface, and it requires the Abaqus CAE user role and also a pool of prepaid credits. This particular user role provides access to Abaqus CAE pre-processing tools as well, which would allow you to build models and do all the things you would normally do within CAE. But in our case, we've done this on site. That's not the problem what we've got. So in our case, we've been using it, or in the trial, as more of a compute service rather than a full end-to-end model generation and solve service. Therefore, we're uploading jobs which are run, and we select various solution parameters, but maybe one just to pay a bit of attention to is the available hardware that's available on the cloud. Typically, in our experience, you choose between solving the jobs on a small node with maybe 4 cores up to a much larger system with modern hardware with around about 144 cores. This decision depends on how urgently you need a particular job to run and which can be balanced against the efficiency with which maybe you draw down your prepaid credits. So as well as just validating this general facility, we had some specific requirements that we wanted to check within the trial of this service before we committed to the December proper session. First of those is that we make quite extensive use in this project of include files, which allows you to split what would otherwise be a single large input deck into a series of smaller input decks that might describe, say, the drone, the target structure, and some setup parameters independently. We've done some tests on these and found that they are supported and indeed work correctly, which is a great tick in the box. Our other requirements were around post-processing, and using the platform, you can post-process results as soon as they're solved. And from my experience, when I tried it, they come up pretty quickly, and you can get, you can animate the results, you can do spot checks as you would when you're normally undertake a normal post-processing activity. However, what we did find was that those Python-based post-processing scripts that we've developed, which are based on local solving, they aren't currently compatible with the cloud service. But as a workaround, we found that actually we can just download the output files and process them on site using the same scripts. I was a little bit hesitant with this initially because the files that we're generating are large. So I was concerned around download speeds, but in the tests I've done, we were getting sustained download speeds exceeding 20 megabytes per second, and this may well have been just throttled by the connection on our end, and that's fine for delivering, for downloading even the largest of files that we've got over in a reasonable duration of time. So overall, although some changes are required to our workflow, the new cloud service is expected to increase throughput of simulation and therefore accelerate delivery. So in conclusion, I will leave with a couple of rather dramatic shots of a recent simulation, a provisional simulation we've got with a propeller striking one of our larger drones, and just summarize by saying that QinetiQ are continuing to use Abaqus to simulate these complex drone collision scenarios. And furthermore, that the 3D Experience cloud service will expedite the generation of these results, and in particular and critically will provide the regulators and our customers with timely input to make informed decisions on these important matters of aviation safety. So with that, thank you very much for your time. If you do have any other general questions around this capability, or indeed on anything related to advanced analysis and test, then feel free to get in contact with me. But otherwise, thank you very much for your attention. And I believe that there is a chat function which we may or may not be able to respond to live, but I'm sure the questions will be forwarded to us. So thank you very much for your time. Bye.